This is Xuan Wang, and I'm going to introduce our project of nuclear instance segmentation across microscopy imaging experiments. The task of nuclear instance segmentation is to detect and segment every nucleus in a microscopic image. An example is shown in the figure below. On the left-hand side is the original image of the cells and nucleus. On the right-hand side is our target. And we can see that the green circles here marks those cells and nucleus that we want to detect in this image. The nuclear instance segmentation techniques can benefit many biological analysis and medical diagnosis, such as breast cancer detection. The approach we take here is to use mask RCNN as our baseline model and further incorporate some data augmentation techniques to improve the performance. The mask RCNN will generate 3 outputs for each input image: a class label, a bounding box offset, and a mask for each candidate object. Mask RCNN defines a multitask loss on each sampled region of interest. It's composed of 3 parts. First is the classification loss of the bounding box. Second is the bounding box loss of the offset regression. And last is the mask loss. The detected mask will serve as our boundaries for the detected nuclei in the images. In addition, we tried several image augmentation techniques to further improve the performance. One example is shown in the figure below. For example, based on the original image, we can do some flipping augmentation such as horizontal and vertical flipping, some affine transformations with different degrees, and also Gaussian blurring on the original image. Then we look at some experimental setup and results. We use the dataset from the 2018 Data Science Bowl. It contains more than 37,000 manually annotated nuclei in 800 images. The training set contains more than 600 images, and the test set contains 200 images. We randomly selected 25 images for the validation set because there's no training and validation split in the original dataset. We also used the validation set for evaluation and error analysis because there's no ground truth on the test set in the original dataset. Here in the figure below, we show some examples of the images in our training set. We can see that the images actually comprised of nuclei with very different appearances that come from 5 major groups of images. Then we show some experimental results we get. Our baseline method, mask RCN, achieves an average precision of about 0.49 on this dataset, while the baseline plus augmentation achieved an improved performance of about 0.52. Here we also show some case studies for error analysis. We can see that mask RCNN make some obvious mistakes, such as wrongly detected the blood vessels as nuclei and also missing some very obvious nuclei. The baseline plus augmentation did much better on the segmentation, but it still makes some mistakes, such as missing those small nucleus and also wrongly detect some background colors as a true nuclei. Some discussion and conclusions. We see that the baseline mask RCN achieves a reasonable performance on this dataset, and the data augmentation further improved the performance. However, a major reason that mask RCN does not achieve a very high performance on this dataset could be that it's actually a very hard task because the training images are comprised of nuclei with very different appearance. Our error analysis further shows that this model can have both false positive and false negative predictions, and the major reason could be that it cannot distinguish the background and nuclei very well. So one future improvement could be to incorporate data augmentation of contrast changes to better learn the features for distinguishing the background and the nuclei.